June 12th. This is the follow-up to video number 12. Uh, this is where I keep my promise to show the math. Worked on the GPS math problem on how much difference the adjustment for relativity makes. Did that in 2015, but didn't have it quite right yet. I believe it was about a year ago or so when I was doing things to complete the book that I went over it again, and I believe I got it right. And so this shows the math. I'm going to hold it up. I tried to read it backwards, but while holding it up, but I wasn't good enough at reading it backwards. Looking into the screen of my phone, looking at the sheet backwards, and reading it. So I'm going to read it, then I'm just going to show it. Here it is. 1,766,477,426,688 inches per day is traveled by a radio signal / wave. First, divide that by 24 to see how many inches radio travels in 1 hour, which equals 42,490,269,112 inches per hour. Divide that by 60 to see how many inches radio travels in 1 minute, which equals 708,171,160,435 inches per minute. Next, divide that by 60 to see how many inches radio travels in 1 second, which equals 11,802,852,673 inches per second. Now divide that by 1 billion to find how much radio travel there is in a nanosecond, which equals 11.80 inches. That's an important number. It's about a foot. Okay, in order to find how many inches of radio travel occurs in a 1/10 second GPS transmission, you need to take that 38,000 nanosecond per day adjustment for relativity and spread it across an entire 24-hour period to see how many nanoseconds of alteration to the system's clocks on the ground at 7 Air Force bases falls into a 1/10 second moment and or time interval. So divide 37, oh sorry, it's supposed to be 38,000. So divide 38,000, I used 38,000 on the the online scientific computer. I typed in 37,000 here, but so divide 38,000 nanoseconds by 24, which equals how much that adjustment is during a 1 hour period, which equals 1,583.333 nanoseconds per hour. Then divide 1,583.333 by 60 to see how much of that adjustment occurs in 1 minute, which equals 26.388 nanoseconds. Then divide 26.388 by 60 to see how much of that adjustment occurs in 1 second, which equals 0.4398 nanoseconds allotted to each. Before the problem can be finished, divide 0.4398 nanoseconds by 10 to see what the adjustment is in a 1/10 second transmission, which is 0.04398 nanoseconds. That's what we actually have in nanoseconds per 10 second GPS transmission, roughly 1/10 of a second. And being approximate here is good enough. I mean, whether this ends up being an inch, a quarter of an inch, a half an inch, 2 inches, it doesn't matter. It all implies the same thing. Now complete the problem by multiplying 0.04398 times 11.80 inches per nanosecond, which yields 0.5189, which is 1/2 inch per 1/10 second transmission. Okay, and here's the math. Here's what I just read. Let me see. I guess I could just post this, at my Facebook page. Anyway. So that's it.